All right, welcome to Physics 4A. This will be an interesting quarter for all of us. Okay, so just to practice here real quick, I see a lot of you have found the chat box already. That's the best way to communicate with me as I'm lecturing, ask questions, things like that. Of course, if too many questions come through, I might miss something. So if I don't get to your question, ask it again. There are also ways to sort of give me a thumbs up or thumbs down if you get something or you don't get it, or things like that. So to provide some feedback in the participant window under more, you can click on that and do a sort of thumbs up, thumbs down, things like that. Go slower, go faster. I'll try to keep an eye on that. And just for practice, maybe give me a thumbs up if the audio is working okay, and you should be able to see the screen that says goals for the lecture. And thumbs up. I'm seeing some thumbs up. Excellent. Okay, so looks like we're good to go. Let me start out by telling you a little bit about myself, and then we'll get into study habits and move through that agenda for today. There we go. So I went to UC Davis, and I majored in physics there. Then I went on to UC San Diego and got my master's degree in physics. And when you're going through school and you meet somebody, right? Maybe you're at a party, they're trying to make conversation. They say, "What do?" You say, "I'm a student." They say, "What's your major?" When you say physics, overwhelmingly, I don't know why people feel compelled to tell you, but overwhelmingly they say, "Oh, I hated physics." And that's a terrible thing. So physics offers so much. Physics strives to explain the world we live in. And there's so many interesting things that we see all around us that physics explains. And you don't have to run to the registrar's office when this class is done and change your major to physics. I understand that might not happen, but I hope you at least leave this class thinking, I can see why people would want to spend their lives studying this stuff. That's the point here. So have an open mind. The more you try to appreciate what physics has to offer, the more enjoyable this quarter is going to be. Physics may be the hardest class you ever take. I don't know. It's not easy, but something has to be the hardest class, right? So maybe it's going to be physics, maybe not. I don't know. But the point is, have an open mind. Look for the interesting things. Look for the topics that you're always sort of wondered about, or how does this link to things I've seen around me all the time, and it makes it more interesting, and you'll have a more enjoyable quarter. All right. I worked in the semiconductor industry after grad school for 10 years, and I found what I did in the semiconductor industry is called process engineering. The silicon wafer that you start out with goes through about 300 different process steps. You're putting something down on the wafer, you're removing something from the wafer, you're creating patterns on there. It goes through about 300 different steps. The company I worked for most of that time deposited an electrically insulating layer. So it was maybe three or four of the 300 steps that a wafer goes through went through our machines. And we deposited that electrically insulating layer. And my job was to optimize that layer, to tweak the ratio of the ingredients, the time, the temperature, the pressure, to try to optimize the properties of that film that we were depositing on the wafer. So I always tell people it's a lot like cooking. And I happen to enjoy cooking also. What does a chef do? They tweak the ratio of the ingredients, the time, the temperature, probably not the pressure, and try to optimize, the taste, the texture, the look of the food that they're cooking. And in the semiconductor industry, I found myself always gravitating towards teaching roles within the company. And so about 15, 16, 17 years ago, I made a permanent change to teaching, and the rest is history. So I've been at Foothill for over 15 years now. All right, that's me. The course, this is Physics 4a. We do mechanics. And so for mechanics, it's a lot of things that we can touch and feel. You can visualize a ball flying through the air. You can visualize things banging into each other, colliding. So from that aspect, I think students find it a little easier than a class like Physics 4b, which is electricity and magnetism, where you can't always picture electrons moving through a wire or electric fields, things like that. So there are sites, if you go to my website and look at some of the links there, the PhET simulations are very good. That's the University of Colorado puts those together. Check those out sometime. But like I said, you might not need them as much for Physics 4a as you do for something like Physics 4b. And the books that are recommended for extra credit, check those out. A Mind for Numbers is very good and has a lot of good study techniques, hints. One of the things that's talked about in that book is it's really important that you do a little bit every day and not, wait to the weekend to catch up. For another reason is that you want to be as efficient as possible, right? You're going to spend a lot of time in this class studying and preparing and trying to figure out the material. You might as well be as efficient as possible and try to minimize that time or get the most out of the time you're spending. And so what does that mean? It means coming into the lecture kind of primed, prepared, having seen the material once ahead of time. And if you look on my pre-lecture worksheets, there's a section there that sort of tries to get you ready for the lecture. And the more prepared you are coming into the lecture, the more you'll get out of the in-class problems and the explanations and the activities we do in class. And then afterwards, we just spent 2 hours learning things. If you wait a few days, that's gone, and you're going to have to relearn it. But if later that day you spend an hour going through the lecture, trying the pre-lecture problems again, trying the problems that we did in lecture, trying the post-lecture stuff that's on that worksheet from my website, then that locks it in. It locks it in so you don't have to relearn it 3 days later, right? And it gives you feedback, instant feedback. If you're having trouble, if you're not getting it, get help right away. Don't wait, because physics builds on itself. We keep going and you're going to get behind and you won't be able to catch up. So every lecture, if you're not getting something, that you've got feedback mechanisms there, all this information, problems I'm suggesting, things like that, that's giving you feedback. Get help right away, get on track. All right. Okay. Speaking of which, I need to publish my office hours. I haven't done that yet, but I will send out the Zoom links. I'll start office hours today at 4 o'clock. Every day from 4 to 5, I think, is my plan, except on Fridays. I'll do an earlier one on Fridays. Okay. What else do we have to talk about? More on study habits. So I think I talked about a number of those things. Those books, though, they have a lot of hints, study techniques. One of the things they talk about is not spending a lot of time at once. You don't have to spend 2 hours in your study session. It's actually much more effective to spend a good solid 30 minutes and then take a break, do something else, because your mind keeps working on whatever it was focused on for the last 20, 30 minutes. After you walk away, kind of free it up, it keeps working on those problems. And you need both of those things. But the key is you have to be super focused on that one thing. So if you sit down to study physics and then ding, ding, your phone text message comes in and you check it, and then you go back to physics and then another text message comes in and you check it and you reply, you're not focused on physics. So you've studied for 20 or 30 minutes, you stop, you walk away, your mind is going to wander to something else, right? You have to be focused 100% on physics for 30 minutes and then go take a walk, make yourself a snack, whatever, and you free up your mind a little bit, and it keeps working on the problem. And actually, it works in a different way. You need both. It sorts out some of the stuff that you can't figure out when you're really focused on it. The example that they like to give is you're sitting in an exam and you're thinking about, problem 4. Oh man, I know how to do this. And you're thinking about it, thinking about it, thinking about it, and you can't get it. And you walk out of the exam to your car and you're driving home, and boom, the answer pops into your head. Oh, that's how you do that problem. I knew that, right? As soon as you free your mind, you focus, think about it for a while. And then as soon as you free up your mind keeps working on it and figures it out. And so when you study that way, it's actually quite helpful. Anyway, I don't want to tell you all the hints in the book, but check out those books if you can. I think they're good. Okay. Okay. Let's start. What else did I want to say? Oh, I wanted to talk about labs. No, I didn't. I'm not teaching your labs. Yeah, check with your lab instructor. Hopefully you've gotten an email from her and you're all set there. I'm not teaching the labs for this section. Okay, let's get going. We'll start talking about motion. So we're going to use what's called a motion diagram. And a motion diagram, the way to think of it, sort of like a strobe light going off. You know what a strobe light is? A light that flashes on and off. So we're in a completely dark room. And I have an object over here, and the light flashes, and you see the object is right here. Then the light goes out, it's dark, right? And then the light flashes again, and now you see the object is here, and it goes dark. And then the light flashes again, and now the object is here, and it goes dark. And the light flashes again, and now the object is here. And so you've seen the object here, 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 right? So a motion diagram that's what it is. The key to the motion diagram is that the light always flashes at set intervals, at a constant interval. So you know the time between the flashes is always the same. So for our motion diagram, we've got a situation like this. We've got a situation like this. The light goes off, we see it at position 1. Then the light goes off, we see it at position 2. Then the light goes off at 3, etc. So take a look at that for a second and let me know what you think that describes. How would you describe the motion of that object in a few words? Okay. Okay, so I'm seeing a few things. I've got let me scroll back up here, hold on. I've got traveling to the right. Travels in a straight line. Linear, constant velocity. Horizontal, linear motion to the right. Okay, so we can all agree, I think, the object is moving to the right. And a few people said constant. I'm not sure what is constant, but I think they mean that the speed is constant. Somebody said constant velocity. I'm going to say with constant speed for now, but it's also moving with constant velocity, but we'll talk more about the distinction. Okay, let's take a look at this one. We've got now a different case. We've got time 1, time 2, time 3, time 4, 5, time 6. How would you describe that motion? Okay, lots of comments coming in. Let's see what some of them are. We've got traveling to the right with increasing speed. I like that. Object is accelerating to the right. Accelerating, increasing velocity to the right. To the right with positive acceleration. Moving to the right with a constant acceleration. Okay, lots of things there we can talk about. Excellent. So it's moving to the right. Oops. It's moving to the right. It's speeding up, right? It's moving with increasing speed. And that means there's acceleration. So acceleration tells us when the velocity is changing. So there is acceleration. There is acceleration to the right. Now let's do one more, and then we'll talk about some of the terminology here. So now let's do this one. We've got no, I went too far. That's okay. Oops. 4, 5. There we go. Okay, I'll do the easy part. Excellent. I'm getting all the comments I wanted. All right, let's go through some of these. Moving to the right decelerating, moving to the right and slowing down, moving to the right with decreasing speed, deceleration, moving to the right, slowing down, decreasing speed, negative acceleration, slowing down. Okay, excellent. So let's talk about some of those terms. So in this case, it's moving to the right and slowing down. Let me just put here acceleration to the left. All right, so it's good. All these terms came out. We need to talk about them a little bit because in physics class, we have very precise meanings for the words, right? Just like if you were, I don't know, taking a law class, there's probably a very precise meaning and difference between words like burglary and theft, robbery. Those all probably mean slightly different things to a lawyer. To me, they all mean the same thing, right? So when you're talking to someone on the street, they use some of these words interchangeably, like velocity and speed. In physics class, we don't do that. They have very precise meanings, so we need to get our terminology straight. So first of all, speed and velocity, let's go through those. Speed is a scalar quantity, right? So it just has a value. You're driving 55 miles per hour on the freeway. That's just your speed, just has a value. Velocity is a vector quantity. It also has a direction associated with it. So you're driving 55 miles an hour on the freeway due south. That's a velocity, right? Speed plus direction. It's a vector quantity. Now, acceleration is one of those terms that we have to all agree on now. Acceleration means there's a change in velocity. A change in velocity. That's what acceleration means. So how can you change your velocity? We like to say your car has 3 different ways to change the velocity, 3 accelerators. It has a gas pedal, right, that makes it go faster. That's one way to have acceleration. You're changing your speed by going faster. It has a brake pedal that makes you go slower, right? That's, you've changed your velocity, you have acceleration. And it has a steering wheel. You can turn the direction. You don't have to change your speed. If you change the direction, you've changed velocity, because velocity is a vector quantity. It also includes direction, right? So any one of those 3 things changes and you have acceleration. Okay, speeding up, slowing down, or the direction changes. You have to have acceleration in any one of those cases. And in physics class, we just call it acceleration. So let's talk about deceleration for a second. I try never to use that word in class, although I probably will once or twice slip, but I try never to use that word. And why? We can all agree. I think if we ask everyone in the class what deceleration means, we would all agree it means slowing down, right? So there's no problem with that, really. We could all agree and just use it that way. But what does that imply about the word acceleration? If deceleration means slowing down, what does acceleration mean? Most of us would say speeding up, and that's not true in physics class. In physics class, acceleration means the velocity is changing. Speeding up, slowing down, or maybe the speed is constant, but the direction is changing, right? Any one of those things is acceleration. So when we use the word deceleration for slowing down, even though we can all agree that's what it means, it sort of implies that acceleration means speeding up. And that is not the way we use the word acceleration in physics class. So I try never to use deceleration. And I try to just stick with acceleration anytime the velocity is changing. Okay. Now, a few people said positive and negative here. So let's talk about positives and negatives, because they know that acceleration is a vector quantity, so they're assigning a direction to it, right? The problem is that they're assuming to the right is my positive direction? I don't know. We haven't defined a positive direction, right? We can make any direction we want to be positive. So if the right is my positive direction, then up here, the acceleration would be positive, and down here, the acceleration would be negative, because in the second example, the acceleration was to the right, and in the last example, the acceleration was to the left. But we didn't define a positive direction, so we can't really say positive and negative. If the left is our positive direction, then this one would be negative, and this one would be positive, right? So positive and negative, we can't really say until we define a positive direction. One thing, one thing that we do know is when the velocity and the acceleration are in the same direction, don't the numbers imply a positive direction? The numbers are just in time. Sorry, that's not like a position on a number line. The numbers correspond to time. Does that help? So my x-axis here, my number line that is indicating position might increase to the right, but the time interval, the object is moving to the left in time. Okay. Okay, so the one thing that we do notice is that when the object is moving in the same direction as the acceleration, when the velocity and the acceleration point in the same direction, the speed is increasing. And when the velocity and the acceleration point in opposite directions, the speed is decreasing. Okay, let's talk a little bit about position. So one of the things we have is a distance and displacement. Question about how do we know the direction of the acceleration. So what we'll learn in a few weeks is that the acceleration and the net force, F equals ma. The acceleration is a vector quantity, and the force is a vector quantity, and the mass is not. Mass is a scalar. So that means that the direction of the force comes from the acceleration, or the direction of the acceleration comes from the force, however you like to think about it. Those have to have the same direction. So what would cause, if an object is moving to the right, but slowing down, what would cause that to slow down? Well, a force must be pushing on it to the left. Otherwise, the object wouldn't slow down, right? So if a force is pushing to the left and the force gives us the direction of the acceleration, then the acceleration is to the left. Does that help a little bit? I know we're not talking about forces yet, but we will. Okay. All right, so we talked about speed versus velocity. Now we need to talk about distance versus displacement. And the example we all like to use is you leave your house, you go jogging, you go out 3 miles, you turn around, you jog back 3 miles, you get back to your house, and what's your, and let's say it took you, how long does it take to do 6 miles? An hour? Let's say it took you an hour. Then you can tell I'm not a runner, right? So you leave your house, you go out 3 miles, you go back 3 miles, and it took an hour. So how much distance did you cover in that time? 6 miles, right? You went out 3, you came back 3, you did 6 miles. What's your displacement? 0. That is correct. You haven't gone anywhere. You're right back where you started. Your displacement is 0. Displacement, you just care about your starting and ending point. Distance traveled, you look at everything that happens in between. Now, let's talk about speed again. Speed and velocity. So what would the speed be for this trip? Speed is distance. (6 miles per hour, right? What's your velocity? Displacement over time. 0. You haven't gone anywhere, right? And the reason is that velocity is a vector quantity, right? So it has a direction associated with it. So for the first half of your journey, you were moving to the right. In my little drawing here, you're moving to the right. And if we call that the positive direction, let's call it to the right the positive direction, you're going positive 3 miles per half hour, right? So positive 6 miles per hour to the right for the first half of your run. And in the second half of the run, you're moving to the left in the negative direction. You're going negative 6 miles per hour. And when you average that out, you end up with 0, right? So velocity is displacement over time, speed is distance over time, and that's one of the differences here. Now, one of the things that we can do is to get the acceleration is to look at these, is to just do a little vector addition problem. So if we have our motion diagram, says here we're time 1, right? Here we're time 2, time 3, time 4. So what's the average? If these time intervals are all the same, then the average speed between 1 and 2 would be that vector right there. That would be proportional to the speed between 1 and 2. The distance between dots 2 and 3 would be proportional to V2 because the time intervals are all the same, right? So all we have to do is look at the distance between these and it would tell us the relative velocity, right? Because the time intervals are all the same. So the acceleration, so the velocity is x2 is the change in position over time, and the acceleration, right, between 1 and 2 is v2 minus v1 over the time interval, right? So let's take a look at this real quickly. V2 is this vector right here, right? So I'm going to draw it. Now I want to subtract V1. You remember how to do your graphical vector addition. When you add vectors graphically, you add them tip to tail, right? So if I was going to add V1 to this, I would take V1 and move it over to here, add them tip to tail, and get them that way. But I don't want to add them. I want to subtract it. So I need to add the opposite of V1. And a vector, what does a minus sign mean on a vector? It just tells you the direction, right? It flips it 180 degrees. So if my acceleration, positive acceleration is this way, then let's say my acceleration was 2 meters per second squared in this direction, I call that positive. Well, 2 meters per second squared in this direction would be -2, right? It just flips it 180 degrees. So I'm adding a negative V1, that would be this one right here, the negative of V1. And when I add those together, this is my resultant, right? So that is proportional to my acceleration. I'd have to divide by the time interval, right? But that's proportional to my acceleration. So that gives me the acceleration. Now, if I did it for 3 and 2, the acceleration between 3 and 2 is V3 minus V2 over the time interval, right? So V3 is this one, 1, 2, 3. And V2 minus V2 is that one. And what did I get for my acceleration? The same thing. So somebody earlier mentioned, and I didn't want to talk about it yet, but somebody in the comments mentioned that this, where were our motion diagrams? One of these motion diagrams, they said constant acceleration. Well, yeah, you're right, I did draw these with constant acceleration. And the reason I know that is that the distance here is 1 grid line on my graph paper. And then the distance here is 2 grid lines. And the distance here is 3. And the distance here is 4. So the speed increased by the same amount every time because the distance increased by the same amount every time and the time is the constant, right? So because the increase was the same every time it increased by 1 grid line. Every time interval, it increased by 1 grid line. The distance increased by 1 grid line, which means the velocity had to increase at the same constant rate. And the acceleration is also constant. If the differences were not constant, then the acceleration would not be constant. But I just happened to draw it that way because it was easy on my grid. So those are constant acceleration. And that's what we're seeing here. One way to spot constant acceleration, you can look at these differences between the each 2 points and do a little vector addition, graphical vector addition problem. All right, let's take a look at this. Just sort of right. Constant acceleration. Okay, so let's take a look at this motion diagrams. Take a look at that. In each case, we've got an object moving from the left to the right next to a tape marked in meters. The strobe flash photograph is taken every second, and the location of the sphere is recorded. Total time intervals are not, the total time intervals are not the same for all spheres. So what we want to do is take a look at this, and we want to find the displacement. Find the displacement for each one. Sorry, we're looking for the displacement over, oh, the time intervals are different. Let's pick a time interval. For the first 2 seconds, how about? There you go. So displacement is always final position minus initial position. So if we're only looking for the first 2 seconds, then let's do A together. X final, let me just write. Displacement is X final minus X initial. So where does it end up after 2 seconds? 4. Where did it start out? 0. So we are 4 meters, and this is a vector quantity, right? So we need a direction. Displacement is 4 meters to the right for the first one. We okay with that? Started at 0, ended up at 4 2 seconds later, right? That's t equals 0. That's t equals 1. That's t equals 2, right? So after 2 seconds, it's moved 4 meters to the right. Displacement is 4 to the right. Good? All right, so now you do the rest of them. Okay, we got B, 1 meter to the right. C, six meters to the right. How about D? Here's your t equals 0, t equals 2 seconds. Eight meters to the right. It was given in the problem. It says, question was, how do you know it's moving to the right? That was given in the problem. Okay, so real quickly, one of the main things, takeaways from this first hour is this: when acceleration and velocity have the same sign, and what does that mean when they have the same sign? They point in the same direction. When they have the same sign, when they point in the same direction, it doesn't matter what it is. Maybe they're both positive, maybe they're both negative. It doesn't matter. When they have the same sign, when they point in the same direction, the speed is increasing. And the opposite is true. When A and V have opposite signs, point in opposite directions, okay, so the acceleration might be positive and you have an increasing speed. The acceleration might be negative and you have an increasing speed. We don't know. Oh, we have to know what sign the velocity is. The acceleration might be positive with decreasing speed. The acceleration might be negative with decreasing speed. We don't know. But once you know the sign of the velocity and the acceleration, then you know whether the speed is increasing or decreasing. Once you know the directions of both, you know whether the speed is increasing or decreasing. Okay, let's put a big red box around that. Okay, let's take a 10-minute break. Get up, stretch your legs, and we'll come back at 11 o'clock and finish up our lecture for today. All right, I'll pause the recording and then we'll start back up at 11. Okay, we are back. A couple of questions came in here over the break. Let's get that straightened out. So the speed and the velocity change together, right? If the speed increases, the velocity increases. If the speed decreases, the velocity decreases, because the speed is the magnitude of the velocity. Velocity is a vector quantity. So the key here, when you're talking about scalars, it's easy, right? A bigger number is a bigger amount, right? And a smaller number is a smaller amount. But a scalar quantity, negative numbers are smaller than positive numbers, right? -5 is smaller than -3, is smaller than 0 when you're talking scalars. When you're talking vectors, that's not true because a negative sign only indicates direction. The magnitude is what you care about for whether it's increasing or decreasing. So a velocity of -5 is bigger than a velocity of -3, is bigger than the velocity of 0. Okay, so a velocity of -5 means it's moving with a speed of 5 meters per second in the negative direction. A velocity of -3 means it's moving with a speed of 3 meters per second in the negative direction. So obviously 5 meters per second is bigger than 3, right? So for vector quantities, the magnitude is what you care about, not the negative sign. The negative sign just indicates direction. For scalar quantities, the negative sign is important. -5, less than -3, less than 0. I think that cleared up the confusion in the chat room. Okay, so I'll just give you a couple of quick examples, and you'll find the change in velocity. How about that? So we've got an object moving with a velocity of 10 meters per second to the right. Let's call the right our positive direction. I'm okay with that. And some force acts on it. And then after that force acts on it, it's moving with 20 meters per second to the right. So find delta V. And I want you first to do it graphically, vector addition. So using vector addition, V final is this one. And the opposite of V initial is this one. Right, that's 20. That was 10. And so what are we left with? -10 meters per second to the right. Now, if you do it numerically, V final is +20. V initial is a +10. And so you end up with 10 meters per second, or 10 meters per second to the right, if we define the right as positive. All right, let's do this one. 10 starts out moving at 10 meters per second to the right, and it ends up at rest. Okay, so graphical vector addition first. Starting off with V final. Then the opposite of V initial. And so starting point to our ending point is right there, delta V. So delta V is 10 meters per second to the left. And if you just do the numbers, negative 10 meters per second. So just a quick little point here. If you're telling me it's negative 10 and you've defined the positive direction is to the right, you're done, okay? Do not tell me negative 10 meters per second to the left. I have no idea what that means. Is negative to the left to the right? I don't know. Okay, if it's just define your positive direction and use a negative sign, or don't use a negative sign and tell me in words what direction it points, or draw a picture, but don't do this. Okay. Let's do one or two more. 10 starts out moving 10 meters per second to the right. That's supposed to be to the right. And it ends up moving 10 meters per second to the left. What's delta V? I'll give you a hint. It's not 0. Okay, we good with these? We do deltas a lot. We do change in momentum, change in velocity, change in accelerator. We look at deltas a lot, so I just wanted to practice a few here. All right, let's take a look at these graphs. So we're given these 6 velocity versus time graphs. For a toy car traveling along a straight one-dimensional road, all the graphs have the same time and velocity scales. So they're asking here for you to draw the corresponding speed versus time graphs for each of these velocity versus time graphs. This first one is negative. It's a little hard to tell. this is your axis, right? This is 0. So it's a constant negative value. The velocity is constant and negative for that first one. Yeah, let's do the first one together. The velocity is constant in the negative direction, so the speed would not be negative, right? Speed is a scalar quantity that's always positive, kind of like time, I guess. So this would be a positive constant. Good. How about B? B would look exactly the same, right? Same graph, because the velocity starts out some positive value, ends up going to 0. Well, the speed is doing the exact same thing. So where are we going to here? Does that look the same? I think that's right. And C? C is going to look just like B does, right? It's just going to flip it positive. We're just taking the magnitude of that. D would look exactly the same. Let's do F first. F would be exactly the same. And now take a look at E, see if you can get E. Yeah, from the first half, oops. The first half gets flipped up and looks something like this. And then the second half looks the same as it does there. That doesn't change. That's not quite right, is it? Something like that. Okay. Now, given those velocity versus time graphs up here, these guys, given these velocity versus time graphs, draw the acceleration versus time for each one. So we're going to have 6 graphs. of acceleration versus time. Yeah, the speed is the magnitude, which is the absolute value of the velocity, yeah. So remember, the acceleration is the change in velocity. So for case A, the velocity is constant, right? It's not changing at all. Always stays the same. It's a horizontal line. So the acceleration would be 0. Now, how about B? So if acceleration is the change in velocity over time, that's just the slope of a velocity versus time curve. So we can look at the slope here, and the slope right here is the same as the slope here, is the same as the slope here, is the same as the slope. The slope never changes because that's a straight line. So the acceleration will be the same at every one of those points. The acceleration will be constant. And the slope is negative, right? It's sloping down, it's negative slope. So our acceleration is going to be constant and negative. The derivative of the other one. Now, that makes sense, right? Because here we have negative acceleration, and here we have positive velocity. And when they're opposite signs, our speed has to be decreasing, right? And is our speed decreasing? Yes. It starts out with some big velocity, some big speed, and it ends up at 0. So the speed is definitely decreasing. So that makes sense. Okay, how about C? So it's going to be constant acceleration, right? Because the slope is the same here as it is here as it is here, right? The slope is the same everywhere because that's a straight line. But the slope of that line is positive, isn't it? So this should be a positive constant value. And let's see if that makes sense. Our acceleration is positive in this region. Our velocity is negative. So when they're opposite signs, the speed should be decreasing, right? And it is. It starts out with a big speed in the negative direction, and it ends up at 0. So that all makes sense. You want to think about that, see if your answer makes sense. Okay, well, let's do the last ones here real quickly. D is going to be 0, right? Just like A. Let's do F. Oops, where's F? F is just like C was, right? The slope is constant. It's the same everywhere, and it's positive. And let's see if that makes sense. The acceleration is positive everywhere here. The acceleration is the velocity is positive everywhere here. So our speed should be increasing, right? And it is. It starts at 0 and it ends up at some greater value than 0. Speed is increasing. So the velocity and the acceleration have to have the same sign. Okay. Now, see if you can put it all together and do E. Remember, the acceleration is just the slope of this line. So how does the slope compare here and here and here and here and here? The slope is the same everywhere, and it's positive. So let's take a look at the velocity versus time graph right underneath it. Okay, so what happened? Here we have negative velocity, positive acceleration, right? Negative velocity, positive acceleration. So what does that tell us? That tells us that we must be slowing down, right? Was it slowing down? Yes, it started out with a big velocity in the negative direction and it ended up at 0, right? This is a big negative number here and this is 0. It started out with a big velocity in the negative direction, a big speed, and it ended up at 0. It was slowing down. Now let's take a look at this region. We've got positive, positive. What does that mean? Speeding up, right? Is it speeding up? Yes, it starts out at 0 and it ends up moving in the positive direction. So it turned around at some point. It started out moving in the negative direction, slowed down, came to rest momentarily, and turned around and went back and increased its speed in the other direction. Kind of like throwing something up into the air, right? If I throw my pen up into the air, it starts out with a big upward velocity, but the acceleration is down and constant. And as it moves up, it slows down, slows down, slows down. It comes to rest momentarily, but the acceleration doesn't go to zero, right? The acceleration is still down. And then it starts moving down faster, faster, faster. Moving with the acceleration, it increases the speed. Moving opposite the acceleration, it decreased speed, came to rest momentarily, then came back down. So this looks kind of like a graph of throwing something up into the air and watching it turn around and come back down. Okay, good. Okay, so our kinematics equations. Let's talk about kinematics. This kinematics means motion without forces. So we're going to talk about motion, but we're not dealing with forces at all. We're just using our definitions of velocity and acceleration, things like that. So, so we have equations. So if we start with our acceleration and say acceleration is the derivative of the velocity, right? In physics class, we like to multiply both sides by dt and integrate. Your math instructors, they don't like that, but in physics, we do it all the time. So we have a dt equals dv. We integrate both sides. And what do we get? We get at is v final minus v initial if a is constant. So we can rearrange this. We'd like to write it this way. V final is V initial plus AT. So that's one of our equations. You can get the other ones using similar techniques and substitutions. So we've got this one. What else do we have? We have X final is X initial plus V initial T plus 1/2 AT squared. We've got V final squared is V initial squared plus 2A delta X. And we've got X final is X initial plus the average velocity times time. Okay, so we've got a number of these equations, and we can use those. We can use those to solve problems. I'll talk about that. So so we can use these, or we can do the problems. X is position, V is velocity, A is acceleration. So we're just talking one-dimensional motion right now. So I'm just using X's, right? But we could use these equations in other dimensions too. We just substitute in an R for X, any position vector. Okay, so let's do this problem, but let's just look at it graphically and see if we can figure out how to solve it graphically. So we've got the minimum distance required to stop a car moving at 15.5 meters per second is 14 meters. What's the stopping distance for the same car moving at 31 meters per second, assuming the same acceleration? So what I want to do is just use my graphical approach to solving this problem. So if I set this up graphically, if I look at the velocity, let's just make a graph of velocity versus time. Right. So when we look at this graphically, we get, if we start at some initial speed, v initial, it takes some amount of time to stop. And if we start at twice that speed, right, we want to know how much time is it going to take to stop. So what do we know about the slope of this line? The slope of this line is the acceleration, right? And we're saying the acceleration is the same in both. So that means that even if we start with twice as much speed, twice the velocity, our slope here has to be the same, which means that T2 is going to be here. And then what's the area under this curve? When we integrate, right? So if we took the derivative of the position versus time, what do we get? Velocity versus time, right? Velocity is a change in position over change in time, right? It's the derivative of the position versus time. So let's just take in generic terms. When you have position versus time, velocity versus time, and acceleration versus time. When you move down, when you go from position to velocity, you're looking at a derivative, at a slope, right? The slope of the position versus time curve is the velocity at that instant. Same moving this way. The slope of v versus t is acceleration at that instant. Now, if we're taking derivatives to go down, that means we do antiderivatives, right? We do integrals moving up. So what's the integral? It's the area under the curve. So the area under A versus T gives us the change in velocity. That's a delta V. And the area under V versus T gives the change in position, delta X. Okay. So let's go back up and look at this problem again. The area under this curve right here is going to be the change in position, right? and it's and what is the area? It's a triangle, 1/2 base times height, right? So we plug in our numbers, and the stopping distance was 14. The time we're solving for, and the V initial was 15.5, I think I said. And so we get a time of 1.81 seconds. And so now we can find the acceleration, right? We can find the slope of that line. Actually, I should call it, should make those negative, shouldn't I? Because it's decreasing, the velocity is decreasing in time. So once you have that information, then you can go back and find T2, right? And then you can use the area of the large triangle to find the distance. Okay, so this is a technique that is kind of powerful. We'll work problems using both the equations, the kinematics equations, and this graphical technique for a little bit and see which one you like better. You know, it's personal preference. There's a key case, a key situation when this graphical approach is really nice. And we'll talk about that more next time. But practice using it. In the end, you end up with the same equations, right? But it's kind of nice. That graphical approach is nice. Okay, let's do this. A car starts from rest, speeds up to 30 meters per second with a constant acceleration over a 10-second time interval. Then it travels at 30 meters per second for the next 10 seconds. And finally, it brakes to a stop in 20 seconds with constant, oh, they use the word deceleration. Bad. With constant acceleration. Which of the following graphs represents this situation for speed versus time. Which of the following graphs represents that situation? Speed versus time. And I got fancy. I set up a poll. Let's see. Hold on. There we go. Which one represents speed versus time? Okay, half of you have responded. Two-thirds of you. Okay, we'll stop it. Almost everybody has A down. Almost everybody put A. A is correct. Just think about what's happening there. We're looking at speed versus time, right? So the speed is increasing over the first 10 seconds. So this one doesn't have increasing speed. This one doesn't have increasing speed, so we can rule them out. This one has increasing speed, and this one has increasing speed. Okay, so far we only have A and D as our contenders. Then it says for the next 10 seconds, it travels at a constant speed. So this one definitely is constant for the next time interval, but this one's not. So now we can rule this one out, right? So the only one that makes sense as you just go through and start eliminating things is A. All right, so now which one represents acceleration versus time? Same situation, same car, same deal. Let me launch our poll. Which one represents acceleration versus time? Okay. More than two-thirds of you have responded, and B is the big winner, which is correct. Because we're looking at the slope of this curve, right? So if this is the velocity versus time curve, and it is, right? We just said that. So the slope of this curve is going to be acceleration. So which one has a positive constant slope? Well, this is positive constant. This is positive constant. We can rule out D. Then the slope here is 0, right? And then the slope here is a negative constant. So this one can be ruled out. This one goes to 0 and then a negative constant. So B is our winner. Okay, so just think about, break it down, think about one thing at a time. Now, same car, same situation. How far does it travel in that 40-second time period? How far does it travel in that 40-second time period? I'll put the problem back up here. How far does it travel? Okay, half of you have voted. I'm going to stop it. Okay, 60%. There are results. Let's talk about this one. This is not as clear cut. So let's talk about this one. Looks like people are leaning toward the high end. Of course, we need to look at, what do we need to look at? The area under that curve, right? So our curve went something like this. Something like that, right? So the area under that curve is 1/2 times 10 times 30. That's, let me color code these. That's this section, right? No, the poles are not graded. And then we've got 10 times 30. That's, what color am I up to? That's this section. And then we've got 1/2 times 20 times 30. And that's this section. And that all comes to 750, I believe. So the answer was none of the above. Okay. Very good. I will post the notes, everything I wrote on the screen. I'll post that as a PDF. The recording will be posted also on my website. The link will be on my website. And then we'll do it all again 2 days from now, right? And then I'll send out an email with the links for office hours. Okay. Have a good day. I'll stop recording now, but I'll stick around for a few minutes if there are questions.